Okay, right. In this video, this is the second part of the Turn on Snubber video series, right? So what's going to happen there is, in this video, right, we are going to derive an expression for the inductance of the inductor L, which will delay the rise of current. Okay, now why is this important? This is important because of the definition of what a snubber is. Now let's revise that definition. A snubber, essentially speaking, is introduced in a circuit as a means of keeping the transients within the safe limits of a device. A snubber, it delays the rate of rise of either voltage or current in a device, and it is used to minimize the power dissipated, okay, during switching. This is why we talk about a turn on and a turn off. That essentially refers to the switching on or the switching off, okay, by means of wave shaping, right? So now back to our objective or our task at hand. We are going to derive an expression for the inductance of the inductor L, which will delay the rise of current, simply meaning there will be a rise in current. However, we want to delay the rate at which this current is rising or increasing to its own state value in a time of t, specifically speaking in our case t1, as we can see on the right hand side of the graph, right? So the first thing that we should notice, or our starting point in this endeavor, it will basically be one thing which we can at the same time view as two things. When I say one thing viewed as two things, it's because remember, here you have a circuit diagram, and then over here you have a graph. Okay, right? So we will start there. So what do I mean when I talk about one thing? When I talk about one thing, the thing that we are going to look at is, we are going to look at VT. Okay? We are going to look at VT. So VT is our one thing that comes across as two things. Why two things? It's one thing because it's VT, simply meaning the voltage across the transistor. Two things because we will find VT on this graph. We will also find VT in the circuit diagram. So that will be our starting point, right? So we are going to use that as a reference point. What do I mean when I say a reference point? This essentially is what I mean, right? What we are going to do is we will start with KCL. We'll start with KCL. KCL simply means Kirchhoff or Kirchhoff's current law, in this case Kirchhoff's voltage law. Alright, so it's KVL. You have KCL, KVL. In this case it's going to be KVL. Now what do I mean when I say KVL? KVL simply means our V supply is equal to our VT plus VL. VL, VT gives us supply voltage. Okay, now there's a set of conditions under which this happens. We will address the set of conditions under which this happens at a later stage, but for now, this will be our reference point. Simply meaning V supply is equal to VT plus VL. Alright, so what we will do is, we will say this is step one. Okay, right. Now, let's move to what is supposed to be step 2, right? What is step 2? Step 2 is we will look at VT. Now essentially, how do I put this to make it simpler? Okay, right, let's do this, right? What we are going to do is the following. We are going to say y equals mx plus c. This is where we are going to work from, because remember, this is a derivation, simply meaning we need to give a step-by-step supposed to be proof. Okay, right? So y describes this function. What is that function? That function, it is essentially what? Y is equal to VT in this context of the graph. So y is equals to VT, right? Then also c is normally the point Nah. C is normally the point at which this line is cutting the y-axis. And where does it cut the y-axis? At point V. Okay, right. So now we will then say C is equal to V. Okay, and then what is X equal to? Again, let's look at this graph. You have a y-axis and then you have a x-axis. In this case, the x-axis, it is a function of what? It's a function or an expression of what? Of time. Okay, so it's an expression of time. So essentially speaking, x is equal to t. Right. Now, what else are we going to be mindful of? All right, let me just do this. Let me do this. Okay, right. The other thing that we also have to note is that m is change in y over change in x. Change in y over change in x. In our case, that simply means the gradient of this line. We can see the gradient will be negative. We can see that the change in y, we can see the gradient is negative, and then we can also see that the change in y is v, and then the change in y, it is equals to v. Okay, and then the change in x, it is what? T2 or t subscript 2. Okay, right. So now we can take all of this and then we can put it back in our formula. So simply meaning we will have y equals mx plus c with this new set of values that we are now going to replace, and then upon replacing them we will find that v subscript t is equal to negative v over t2. Okay, and then what is our x? Our x is basically t, and then we have v, and then we can just go and then we can rewrite this vt is equal to, for now let's make it v minus, let's say t over t2 times v. Okay, right. And then this will be our number 2. Right. So now, what are we noticing? What we are noticing here now is the following. We are noticing that according to KVL, right, Kirchhoff voltage law, V is equal to Vt plus VL. That part is understandable, meaning it's digestible, mathematically speaking, okay? Then also, from the graph, we've deduced the following. Vt is equals to V minus T, okay, divided by T subscript 2, and that multiplied by V. Note, the gradient is negative because it's a declining or a falling gradient, okay, or a decreasing gradient, okay, right, or a negative gradient, right, negative slope, okay, right. So we have that sorted. So what will the next step be? The next step essentially is now going to be the following. When you look at this diagram, you'll notice that there's an inductor. Now, what can you tell me about an inductor? The thing that we should notice about inductors is that an inductor, what happens in an inductor? In an inductor, current flows via an inductor. Okay, it flows via an inductor or through an inductor, and then in the process, it builds up what we call a magnetic field, and that magnetic field, at a later stage, it takes us in a direction where we can talk about the magnetic flux of the inductor. Okay, now this magnetic flux part, That's where we are now going to delve into. Okay, so what's happening there now is we are going to take, in this case, IL. Okay, right? IL. Why IL? Because it's the current going via the inductor. So it's I, current going via the inductor, IL. So the formula for this now is basically 1 over L, and it goes from 0 up until T1. Now why does it go up until T1? It goes up until T1 because that's the point at which IT becomes IL, meaning I supply. Also, that's the point at which IT reaches a type of saturation. That is why we will notice that there's a sort of plateau happening. Okay, now normally we talk about a choke. Okay, so right, so be mindful of that. Right, so as we proceed, and then this here will obviously be, if the current is described via the inductor, then the voltage should also be described as a function of the inductance, meaning VL, and that obviously dt. Right, so now what's going to happen is the following. What's going to happen is we are now going to substitute values. Now, part of the reason why we have to substitute values is to replace VL in this equation. Now, if you look at this, what do you notice now? You will notice that somewhere here there's a VL. You will also notice that somewhere here there's a V. You will also notice that somewhere here there's a VT. Now, there's a reason why I use words like somewhere. Somewhere simply means there's a relationship between VT as well as VL. Okay, right, as we've noticed in equation number 1 or expression number 1 here at the top. Right, so what will be the next step? The next step, it will basically be to say the following. This will be the next step. Okay, right, let me just write it here on the side. VL is equal to V minus VT. Okay, what do we know? We know that we have VT. That's equation 2 up here. So now we will say VL is equal to V minus VT is equals to V minus T over T2 times V. Therefore, we can conclude by saying that VL is equal to V minus V plus T over T2 V. Okay, we'll then also notice that these cancel each other out. So essentially speaking, our VL is going to be equal to T divided by T2 times V. Okay, right. So what are we going to do with this value? What we are going to do with this here, this expression, is we are now going to substitute that in here. Alright, so now we will have IL equals to 1 over L 0 to T1. VL is just V times T over T2 dt. Okay, right. What we will also notice is the following. We can say IL is equals to I over L times V over T2 the integral of 0, it's a definite integral to t1, okay, right, of t dt. Now this shouldn't be that difficult. IL equals v over L t2, right, times. Now when we integrate this, we are going to find t1 squared over 2. That's what you're supposed to find over there. Okay, right? Now notice, what did the question say? The question said derive an expression for the inductance, meaning L, which will delay the rise, da 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 da, right? So simply meaning derive an expression for the inductance. And in this case, we have sort of, or supposedly, or seemingly derived an expression for the current flowing via the inductor. However, there is the inductance. Okay, right? So this is what we are going to do. So now we will say, or therefore, L is equal to V times T1 squared over, okay, IL2, right, as well as T2, and then this formula here, or this expression, is basically the answer to our question.